Hello students, welcome to lecture 6, called Noise and Error. In the previous lecture, we introduced the VC dimension, also known as Vapnik-Cherbanenkis dimension. And we said that learning is possible if a given hypothesis have finite VC dimension. And also, we have large amount of training data and low in-sample error. Using the VC bound, unknown out-of-sample error could be upper bounded by in-sample error and model complexity term. In the previous lecture also we used VC dimension to characterize the model complexity and also briefly discuss about the VC and its relationship to in-sample error and out-of-sample error of a given hypothesis class. If we have a hypothesis with a higher VC dimension, then that in-sample goes small. However, the second term goes up, which is model complexity. If we choose a hypothesis with a small VC dimension, the second term model complexity will be small, however, the in-sample error will be high. In this lecture, we move on and introduce a new topic called noise and error with the following outlines. So noise and probabilistic target function, error measure, algorithmic as error measure, weighted classification. Let's recap the learning flow with different components as we already got used to them. So this learning algorithm hypothesis set makes our model, training examples, final hypothesis set, and unknown target function with our assumption that our training examples are generated by some unknown but fixed probability density function. What if there is a noise in the data? In our training examples and also possibly target function plus noise. When we introduce pocket algorithm, we have seen this example. Given data that correspond to two different classes, we see some points are misclassified as follows. What if these points are actually some noise due to mislabeling or measurement error in the data? Can VC bound work under noise? So we describe these points as example from credit card applicants, okay? For instance, age, gender, annual salary, and some other information. Well, we can have three different cases that can explain possible cases why these 2 points are making the data more complex or not linear separable. So in the first case, we can have noise in Y, right? In the label provided here, for example. So it could be a good customer, which is mislabeled as a bad. This is possible because all of these labels are eventually given by some human, some expert who is labeling them good or bad. Similarly, noise in Y can be explained as they're same customers, but for some unknown reasons, they were given different labels. One of them is good, the other one is bad. Or we can also have a noise in X, some inaccurate information about the customer, also possible. For instance, maybe there is one more zero added by mistake. Given these possible cases scenarios, does VC bound work? Let's revisit the probabilistic marbles example. Initially, we were interested in probability of orange marble happening. And that event was related by the h of x not being equal to f of x. While green marbles were related to h of x equal to f of x. We were interested in finding the probability of this event happening. So in deterministic case, if our marbles are deterministic, with some probability distribution, the deterministic color will say yes and no. So we have some unknown target function and then hypothesis that we can provide deterministic answers. Either this is true or false, right? While in probabilistic case, we have marbles with the same unknown but fixed probability distribution The noisy targets can be related to probabilistic color, not deterministic, where we assume that the true labels are being generated by some probability, conditional probability. So P of Y given X. Right? So both have same nature. In both cases, we try to estimate probability of orange marbles if and only if they are IID, independently identically distributed. So VC dimension holds for X being generated by some unknown probability distribution in IID case, so independently identically distributed, and Y also IID distributed by some other probability distribution. So VC holds if these assumptions are met. We can consider this P of Y given X as target distribution. Instead of target function, we now talk about target distribution to account for possible noise in data in Y, which characterizes the behavior of mini target on 1x, one given example. Right? Also, we can also view these as ideal mini target plus noise. Right? If we assume that the probability of blue circle given X is 0.7, the noise part probability of cross given X will be 0.3. So this could correspond to ideal mini target on given example plus noise, right? So ideal mini target plus noise. And the noise could be related to, let's say, some flipping noise level. While deterministic target function will correspond to a special case of target distribution, where the target distribution provides exact answer, 1 or 0. Okay, very confidently true, 1 or 0, when we have given Y equal to target function or not equal to. Then the goal of learning is to predict ideal mini target on often seen inputs with respect to P of X. We can introduce some changes in our learning flowchart, in particular here. While initially we said we have ideal unknown target function, now we are saying that it is actually an unknown target distribution, which represents unknown ideal function plus noise, which is in turn generating the Y's in data. Okay, this component is not new. We needed to assume that every example is being generated IID in order to use the Hoftings and VC bound. So Y, so this is the Y's of the training example, and these are the Y of the future example and examples. So the learning algorithm remains same, and we have same final hypothesis component in place. Now let's talk about error measure. When we select final hypothesis, G, and quantify if it approximates the unknown target function, we are usually talking about the out-of-sample performance of the G. We can take the expectation of the all unseen example. So more generally, the error measure or error function can be out-of-sample error, which again of average over unknown X, and can be a pointwise error function, which is evaluated on one X or on every individual X. Right? And then the error measure can also be the classification. Well, we have seen these brackets so far, which quantifies if the prediction is equal or not equal to target. If this is true, then the output of this classification would be 1. If this is false, then 0. Therefore, we called it as 0-1 error, classification error. we can express E, the error measure, as averaged over several errors on a pointwise evaluated error. Like out-of-sample error, for example, is an expectation over distribution of this error, individual pointwise error. We call this type of error as pointwise error measure. In in-sample case, it's easy to understand. So pointwise in-sample error consists of the averaging over n examples of each individual error on each individual point. For example, if you have 10 points, we take the error on each individual 10 point and sum and average. This we are basically performing a pointwise error measuring and averaging. While out-of-sample error will consist of the expectation of all similarly pointwise error. So we will mainly consider pointwise error simply just error. There are two important pointwise error measures that we use in learning. Usually we denote y tilde as the estimate or predicted label or target value, while the y as the true distribution, the true label or true target value. Okay, the output of g will be considered as y tilde. So 0-1 error function will use or will calculate 0 and 1. Okay, so if y tilde is not equal to y, true y, then the output will be 1. If this is false, if y tilde is equal to y, then you'll have 0. Basically, it's a correct or incorrect answer, represented by 0 and 1. And most of the time, we use this for classification problem. While there is another very popular error measure called square error. This is error function that basically subtracts the predicted error, predicted y tilde from the true and squares it. We can use this error function to answer how far is y tilde from true y. Usually, these kind of questions are relevant to regression problems. Next, how does these error functions guide learning? These error functions help us to select the proper or correct g that approximates our target function, and we use them as one of the metric criteria for algorithm to select from our big hypothesis set. Okay, that is one of the examples of how error function can guide in finding the best hypothesis. We can add one more component to our learning flowchart, which is the error measure we just discussed. Now the algorithm can select hypothesis and see its error performance. Okay, so now we have one more component. The VC theory works for most hypothesis and or most error measure or error function. The choice of error measure is also very important in different applications of machine learning. So let's consider this fingerprint-based verification entrance to your house. What does it do? So we have fingerprint as a form of input to the ideal target function. And in correct cases and ideal cases, we should have +1 identified you and let you inside the house, and -1 identifies as intruder. Okay, based on this fingerprint. And you acquire data from, let's say, from yourself, a lot of samples of fingerprints, and then you train your algorithm or function of your choice. Then you select the G, right? So when we evaluate the G, we can face two different kinds of errors: false accept and false reject. What is false accept? So assume that this is our F, ideal or the true values, okay? +1, -1. And then the possible outputs of your learned G from your fingerprint data. When F agrees, okay, we are interested in this intersection between this row and the column. No error. In this case also, F is -1, your G given input also provides -1, no error. False accept is a case where the expect true value is -1, but your G gives +1 as output. In other words, your G identifies intruder as you, or it identifies some other fingerprint as you by false accepting you inside house. Let's put it in that way. False reject means it rejects you. Actually, the true value is +1. However, your G says it's -1. So you scan your fingerprint, pass through your G, but your G doesn't let you in, and it identifies you as intruder. So it is called as false reject. So in this specific example, the 0-1 error penalizes both types of errors equally, which could be a problem depending on some applications. First of all, you don't want some other strangers enter to your house, so you want to minimize false accept in your home entrance system, right? So let's some other examples. For one of the application of fingerprint verification can be used in supermarket application that is giving out discounts. So the idea is the customer comes to your supermarket and receives discount if his or her fingerprint is recognized correctly. Otherwise, will not get a discount. So the role of false reject and false accept here is different. For example, so false reject will lead the customer unhappy or make the customer unhappy. And then that customer may not return to your supermarket. Okay, if you falsely reject, if your hypothesis that cannot detect the customer as customer, right, +1, but here it is -1. False rejecting can cost some money to the supermarket. While false accept, okay, is related to, okay, making a mistake. Okay, so the true value is -1, but your G says +1. Well, in this case, you just give away a minor discount. The supermarket can lose some discount, some small loss. However, you got the fingerprint of intruder, possibly. So, why is this application is given here? Because the role, false accept and false reject, right? So we want to make sure that the system, the fingerprint verification system, makes few false rejects. Because you don't want to lose your customer, and we don't want unhappy customers. So even if you make more false accepts, okay, by losing some small minor discount, giving away by small minor discount, we need to make sure that the system makes as few false rejects as possible. One of the solutions to this kind of problem is to apply some weighting. In other words, we can design our error function or this confusion matrix. This is called as confusion matrix, where the false reject rates are higher. So this is, if you want, we can understand it. We can tolerate up to 10 false rejects. So if we intentionally increase, apply some weighting related to false reject, then During the learning process, our hypothesis or learning algorithm will try to pick the G which is more tolerant to making few false reject mistakes. Let's take another example where fingerprint verification is used for CIA entrance, CIA building entrance. So idea is same. So we have the fingerprint verification system installed at the entrance to the CIA building. And then the idea is to accept CIA agents versus non-agents, anyone else. And now let's take a look at how false accept, false reject can affect this application. Now, for example, this is our confusion matrix. Okay. So in CIA application, if we make false accept, we may end up with serious consequences, right? Because we don't want anyone else except agent to enter that building. Okay? While false reject is a case where a CIA agent will not be allowed in the building for a few times until you try to put your finger on that recognition system a few times as a CIA agent. So in this case, more weight should be given to false accept. So false accept should be penalized. We don't want to have false accept case increase. So we can penalize. We can introduce some weighting. Okay, this is a confusion matrix. So we want to make sure that the hypothesis that we select is strong against false accepting. So makes fewer false accept. So it is application specific. For CIA case, we want to make sure that the system makes less false accept. While in supermarket case, we want to make sure that our error function makes less false reject. In CIA, less false accept. So the error function, error measure, should be designed in an application-specific way. So we can take a look at the updated learning flowchart that we have been building so far with the algorithmic error measure, which is located here. Now take a look at this question. Let's consider the error function below, designed for CIA building entrance. What is Insample Error when using this error function? This is the confusion matrix designed for CIA build. We know that this is related to false accept, false reject cases. So now we need to identify one of these as Insample Error. As you can see, the correct answer is 2, which consists of averaged across n number of examples, pointwise error measure for all +1 classes, +1 classes, okay, +1 classes, and we collect all those mistakes made by negative ones, okay, actually for these negative ones. This one is for positive ones. So we can see that Insample Error can be designed in the following form by applying some weights. If you are more strict, you can increase this number to 2000, 5, or 10,000. So when we have -1 yn, the false positive made on that example is penalized 1,000 times more. So take a moment and try to understand why that's the case. Why not 3 or 4? What is 1 here? Following, let's take a look at weighted classification scenario. We considered CIA example in the previous quiz. So CIA application should involve minimizing these false accept rates. Therefore, we can apply some penalties, some weights, so that the hypothesis that we are learning or estimating from data will be more strict against making false accept mistakes. We call these a matrix, sometimes a confusion matrix for binary classification tasks, or also cost matrix. You can also call it as error or loss matrix, but mostly we use a confusion matrix. Okay, based on this confusion matrix, we can try to come up with two error functions out of sample error, insample error, which will incorporate these weighting or penalty. So out of sample error will be based on penalizing mistakes that relate to false accept, which is the case when we have y is -1. However, our hypothesis makes mistake on that point. Similar, in sample error will have the weight here. Well, here we don't know this p, therefore it's hard to calculate expectation. But in sample case, we again can calculate in sample error based on the training dataset available. Also, we can penalize the cases for false accept when our hypothesis makes a mistake. When this is true, that means for negative ones, then we penalize it. We can call this as also a weighted modification of classification, which result in different weights for different examples depending on -1 or +1, one of two. Let's now talk about possible connection between in-sample error, which is weighted, to original 0-1 error that we used in perceptron learning algorithm case. So the original problem in the weighted classification consists of penalizing more on false accept cases when h of x makes a mistake on these examples. Okay, false accept, false reject. So assume that our dataset consists of the following n examples, and we have fewer number of negative examples. So how can we make sure, or how can we connect this problem, weighted classification problem, to original 0-1 unweighted in-sample error? So one possible way is to make multiple copies of all examples 1,000 times, negative examples I mean, in the new dataset, and use the original unweighted in-sample error function. Okay, so the idea to connect this weighted classification to original in-sample error, unweighted classification, to make these negative examples appear more frequently during the learning process. Okay, so we copy negative examples 100 or 1,000 times, so that in-sample weighted for left-hand side will be equal to original unweighted 0-1 error for right-hand side. I mean equal during the learning process, during the weight update. To summarize this lecture, we have seen different types of possible noises and then error measure or error function cases. We said that noise and probabilistic target can replace the original ideal target function. So now we assume that our target function is actually the target distribution, P of y, okay, given x, that incorporates the probability of noise in the data. And also we mentioned about error measure, which in turn affects this ideal target function. We also said that algorithmic error measure should be application or user dependent. Okay, we briefly talked about weighted classification, and one of the examples was given some unbalanced data with one class having more examples, we just can replace or copy virtual examples. Okay, so in the coming lectures we'll see some more algorithms and the different types of error functions.